problem. Different vertical search engines have unique characteristics. For example, news. News have the problem is we need to combine the relevance and freshness. The similar idea, I mean, is already covered by the web search freshness. So I will skip this part. The next part is related to local search. So local search relevance is different. Because on web search, we believe, given a query, like if a query is Yahoo, we know exactly, what his user want. And for something like news, it is a little bit more complicated, but just the query, just the relevance and the freshness, it is still easier. But for local, at the beginning, right, we're trying to provide some MR models, provide some ranking result, but the user don't like it. So we spend quite some time to figure out what is the relevance mean for local users. And finally, we'll find for local users, user want three almost orthogonal dimension of need. First is text matching. For example, if people want to search a query like a Japanese restaurant in Sunnyvale, where Yahoo is located, or a similar query like a Japanese restaurant in Bangalore. So the user want to find the Japanese restaurant, right? If the result is about an Indian restaurant or Chinese restaurant in Bangalore, user don't like it. So text matching provides the basic need, but just the text matching is not enough. For local result, user have a lot of expectation on user rating, right? Sounds like for restaurant. If I go to a new place and want to find some new restaurant, I would look at the user rating. And I'm more trustable high rating restaurant instead of low rating restaurant. And also distance is very important. So because in Bangalore, it's a big city, but think about in Silicon Valley, in Sunnyvale. Sunnyvale actually is a very small city, only have tens of, I think have like 10,000 people, and it's a small city. And it has some other cities very close by. If people search Japanese restaurant in Sunnyvale, and if there are some very good restaurant in the nearby city, it's also acceptable for users. And this type of distance is also query dependent. For example, if I search a restaurant, maybe I want to search the nearby 5 kilometers around, right? But if I want to search something like a car dealership, because different car dealership have big difference of the in terms of price, so I can afford to go like 50 kilometers to go to a different dealership. So distances are also a very important factor, which means given a local query, we need to consider good text matching. We need to put the high-rated result on the top position. And we also need to consider the appropriate distance. So how to combine different dimensions into one dimension? So we formulate the problem as learning with multifaceted. Because for recency ranking, we just trying to combine the relevance and freshness with some heuristic-based rules. But here, as we have more dimensions, this kind of rule doesn't work. Rules, cannot properly reflect more dimensions. So as a result, we're trying to provide separate models for text matching, user rating, and distance. Then, based on the user click, learn a preference model, that is pairwise learning model, to trying to combine 3 dimensions of the ranking scores. So that is the main idea for local search ranking. And another part is for transfer learning ranking. So transfer learning ranking on vertical is much more difficult than in the web search. Because think about in web search, ranking on US market or ranking on Japanese market, there's something similar. There's something different. But on vertical search, the problem is much more challenging. In terms of the transfer learning, for example, we have a lot of training data on, for example, on news search. Now we want to solve like answers search problem or tweet search problems. How can we transfer the common knowledge across different ranking tasks together? And if we have a good algorithm, first it can save a lot of editorial resources. And the second one is it will be more robust, and it can be applied to many other ranking tasks. And there are different level of transfer learning, like algorithm level, data level, and feature level. And this part, we are mainly focused on the algorithm level. So here is one example particularly meaningful for Yahoo. For example, we have Yahoo have news search, right? So we ask editors to collect a lot of training data to provide us the news MR for news. Then have Twitter search. We ask editor to train the data again to get some training data for Twitter MR. Then train a Twitter MR model. Similarly, we get a MR for answers. We have many other properties, like for example, for sports, right? Can we, try to avoid request any extra training data, just the transfer knowledge across different existing properties? Because if we can leverage the common knowledge across different properties, first is we can save a lot of editorial resource. And the second one, this kind of model will be very robust because it's already consider the different characteristics of different properties. So here is the basic idea. First is this problem is very, very challenging because the feature dimension is totally heterogeneous. For example, we compare the news search and the Twitter search. And we find that on news, right, for each news article, first is on news article, maybe the anchor text or page rank is less important because, for example, most of the news are within Yahoo or like within BBC, So for news, we have title section, abstract section, and body section. But for Twitter, there is only one section, right? Just a small tweets. And for news, we have news source or authority information. For example, if a news is from Yahoo, maybe we believe it is more trustable. If a news is from some blog site, right, maybe it's less trustable. And Twitter don't have any source or authority information, but Twitter also have some social network, right, because it has some retweet relationship and follow relationship. For news search, for example, in our data set, there are hundreds of features. For Twitter search, there are hundreds of features. But compare these two, only 7 features, they are common features. So majority, dominant features, they are different, they are heterogeneous. However, we can still learn some knowledge which is transferable knowledge across different properties. For example, if we compare the news search and the Twitter search, we find that is the text matching, the proximity, the proximity between the query and the tweets, and the query and title, or the query and abstract, they are transferable. And similarly, we find the user favoring authority news site like Yahoo or NBC, right? And the user popularity information on Twitter social network based on page rank, they are transferable. They provide some signals, although they, different features, they are different, but they are signal, they are similar in basic. And finally, we provide transfer learning knowledge with some domain knowledge. The basic idea is we still cannot provide one MR for which means not all ranking problems, not all vertical search problems, they are transferable, but we can group them into several big categories. For example, for news, sports, finance, and Twitter, they are all fresh, sensitive, recently related. So the different tasks within the same category, they are transferable. And for answers like government search, university search, they are not related to time sensitiveness, so they are transferable. There are some listing problems, something like shopping and local, they are similar. For example, text matching, they are similar. User review, they are similar. But maybe for local, distance is more important. For shopping, the price is more important. So this type of information are more important. So the basic idea for this transfer learning, although the feature set, they are heterogeneous, but we find there are some signals, they are transferable. Then we can mapping different feature into some latent space. For example, we mapping the text matching between query and tweets and query and title across different properties. We mapping them all into some latent feature space we call text matching. And we mapping the news site authority and the Twitter account popularity into some latent space. We call something like popularity features. And then we can learn some model onto the latent space. And this kind of latent feature actually is a combination of some existing features. And finally, we can leverage the information across different properties and to learn some transfer learning algorithms to different new tasks. And those kind of domain knowledge can help transfer learning property. And then we can convert the feature into the latent feature within the category and apply the machine learning ranking algorithms, something like point-wise or pair-wise algorithm, and provide some good ranking result. For example, we did some study based on news and Twitter. And here we find that news search have smaller data set, training data set, and Twitter have more training data set. So although there are very little common features, and we find if we leverage all and here the source property, for example, for this task is we have more training data on Twitter, and we want to use the Twitter training set to improve the news training set. For example, if we only have 1,000 training set for news, the baseline result is just to use 1,000 training data on news. The result is not good. But if we can use the transfer learning algorithm, we can improve the DCG for 8.8%. So as the total amount of training data on news set increase, the effectiveness or the improvement of the transfer learning decrease, but they still have significant improvement. So similarly, we have another example. For example, we're trying to improve the data set from the Japan market, although they have different language. But if we can mapping those kind of features into the latent space, we still can leverage the Japan answers training data to improve the US news ranking task. But as here, the common feature is even less, only one common features. And the improvement is smaller than the previous one, because the similarity between US news and Japan answers is smaller than the similarity between US news and US Twitter. So as a result, that is also convince our previous finding that we need to first use some domain knowledge to categorize different tasks into some of their groups, and trying to leverage the similar task within the same group, which is more transferable than other tasks to improve the ranking result. Okay, so that is my presentation. So there are some time and for question answering.
My question is about just the last part.
Okay.
Mostly in terms of, is this problem actually is this more of a domain adaptation problem than a transfer learning problem? Because the eventual model that you are training for the learning problem is the same, which is the ranking task. The feature, however, are coming from, or the data distribution is different, is what I suppose is being emphasized here.
Okay, so first is, I would say, the boundary between the adaptation and the transfer learning first is vague. But in the learning to rank community, adaptation is more like to say, if two tasks, they have many similar features. For example, if I want to provide a ranking for US web search and provide a ranking for Japan web search, they have, most of the features, many features they are in common, but some features they are not the same. So this part we call it's more like adaptation. And for the vertical search, because the feature set is totally different. So in this community we call it more like transfer learning.
I see. But the optimization problem remains the same.
I was just curious, what is the most profitable vertical search product?
What is the most what?
Most profitable vertical search product?
Currently, within Yahoo, I mean, the most important is differs over time. For example, 2 years ago, the most important one is local, because at that time, Yahoo Local make $100 million per year. And I think recently, most important one is Yahoo Shopping, because Yahoo Shopping would like to make $100, $200 million, by the end of next year. And in terms of profit is one issue. Another issue is in terms of the page view and user engagement. For this type of issue, Yahoo News and Yahoo Finance is very important.
I have a couple of questions. On the transfer learning, right, the motivation seems to be that to avoid generating a fresh set of editorial judgments for the new model that you're trying to train, right? But since even with transfer learning, there are only a subset of features that are common for which you can transfer the feature weights, you have to still learn the feature weights for the other features, right, in your new model. So you'll have to still anyway generate training data and editorial judgments, right? So,
right.
I mean, I'm not able to connect the motivation with how you achieve that end goal.
Okay, because in this example, we just show the importance, the effectiveness given different amount of training data. But for example, think about if we have a new property, right? And we want to provide our ML model as soon as possible. And at some times, there are some editors, they provide 1,000 editorial judgment. Then we can leverage other existing judgment from different properties to improve the result. Actually, in later, not in these slides, because in some of our experiments, we're trying to reuse the editorial data from web search to improve the vertical search. Because on web search, we have millions of editorial labels. If we can, since we successfully reuse the training data from the web search, so which means we can always provide some reasonable good result very quickly and efficiently. For example, some of my team members currently working on answers ML to improve the answers ML. That is trying to reuse the data from news and web search. And it will, because I mean, existing editorial data, they can provide us very strong signals in terms of relevance. So that is very important.
Got it. So the second question is regarding the previous section, which is on the recency ranking for time-sensitive features. So the main problem is like for the aggregate features which are time-sensitive, you don't have enough signals for new URLs that are starting to come in, right? So I understand the discovery part of it, discovering the new URLs, definitely using the Twitter source is one thing. But I was just curious to know, is there any attempt to actually, for example, seed the aggregate features using other features like, let's say, host rank, right? So instead of you don't have click features or the page rank for that particular URL, but what if you actually seed those with other host-related information, right? Assuming that news-worthy queries are going to be served mostly from top-quality news sites, can you not seed it with existing aggregate features at the host level and then see how that model performs compared to, let's say, having a separate recency model and blending it?
Yeah, it's a very good question. So generally speaking, I mean, for some of the news articles, if it is, for example, let me give you an example. When Michael Jackson he died on that day, the news article sometimes is there are some delays. So at the beginning, it is spread out in some like Twitter or forum. So if some news articles already published, so we already can trust the news article. But sometimes the challenge is even before that, there's some gossip from the Twitter. How to handle this type of information is really challenging. So yes, we can handle those type of domain, host level features. But sometimes if an article, his host score is low, or sometimes it's less trustable, we, need to be more cautious about that type of features.
Thank you.
In the section where you were talking about the competition, you on a slide you had that the ERR metric has higher correlation with user metrics than NDCG. So what kind of user metrics are you talking about there, and do you have any ideas about why ERR correlates better?
So here is some background information because my colleague, Olivier, he is the inventor of the ERR metrics. So part of the reason is we put the ERR as the official metrics on the competition is trying to sell the new metrics, evaluation metrics. So ERR, generally speaking, has more correlation with the user click information. And DCG or NDC is purely based on editorial-based method. So actually, there are a whole family of different evaluation metrics. And I think George, one of our colleagues, he will present more about different types of metrics in general, I think, later this week. Okay, but I mean, if you have interest about the ERR, so I would recommend you to read the paper in details, and it introduces why the ERR is believed to be a better metrics. But I think nowadays ERR, the community is starting to use it, but I still believe the most popular, the standard metric still like NDCG.
So again, a question about Twitter. So Twitter signals could be quite noisy, as in the URLs that become popular on Twitter might not always be what everybody wants on a web search. So did you ever encounter challenges there?
Yes, yes. So first is we find that majority of the Twitter information, they are spam. So which means in our studies, we use some very strict rules to only consider the small portion of the, we believe, higher quality of the content. But I still believe Twitter is important because think about when there are some breaking news happen, right? Sometimes there are some breaking news, Yahoo do not have any news about it, and NBC don't have any news about it. We only can get some information from the Twitter, from this kind of gossip. And Twitter can provide some really
I wanted to know how do you rely on the user ratings? I mean, that could be manipulated, right? Someone might simply be trying to beat the system and show that you can actually fake the reviews and stuff. So how do you differentiate between the actual user ratings to
okay, so you mean, for example, the user rating within like Yahoo logo, something like that, right?
yeah, that or like what we see, what we are seeing on screen right there?
Okay, so for that one is, I think first it's a very important question, and it is on our calendar, on our schedule, but we are not solving it yet. So generally speaking, we can leverage some other information because think about all the Yahoo reviewers, right? All the Yahoo rating information, they have a unique Yahoo account, which means we can, learn the user's signals from different behavior. So very likely, if a user is a trustable user, and he would like to make comments on local, he is a reasonable user on other properties. If a user he making spam on some other properties, very likely the trustness on local is less important. And there are some other users, he do not make any comments on any other property, but make tons of comments on local. And for example, just on a few restaurants, very likely he is trying to spam the gaming system. So generally speaking, we can leverage the user signals across different properties within Yahoo to provide some actual signal to provide to provide some trustfulness or authority for the user reviews.
Yeah, I'm not sure how much is this relevant to exactly this talk, but how much of the, looks like, a lot of clues about the search engine you have given in this talk. So the more signals that you take from the web, you give out in the public, the more people can manipulate the search engine, right? So isn't it fair that the algorithms of search engine are actually hidden from the public, or how much of the signals should you reveal?
Yeah, I think that is something I want to say, but to some extent I forgot to mention. After the Yahoo Learning to Rank competition, so one of the major conclusions is ranking algorithm as a kind of research direction is quite mature. So as a follow-up, for example, before the competition, Yahoo Labs have a relatively large team focused on improving algorithm. At some time, I remember we have more than 10 people trying to improve the algorithm. But with the competition result, Yahoo Challenge, Learning to Rank Challenge result, we believe, well, maybe it's not necessary to put so many people trying to improve the algorithm, because the improvement space to improve algorithm is very, very limited. Instead, feature, ranking feature, provides the most signals. So that is to say, if we want to improve the ranking result, for example, web search, the more important provides some actual signals. So feature engineering, in the past, most of us believe that feature engineering is less cool than algorithms. Algorithms seems to be more cooler than feature engineering. But one of the